period of time this program, which appears to be a very interesting one. It is unfortunate that Professor Weiss was originally scheduled to speak on such topics, has not been able to come, but I am glad that to have the opportunity myself to present you some questions and the results that I have been working on for quite a few years, and which I find quite interesting. So today's session will be introductory in character, so I will devote it to presenting the problem in some details and to give some sort of overview of what is known about this problem and what are some of the important open questions. So there are two closely related problems that I'm going to speak about. So they both involve water flows with the free surface, and they can be either two-dimensional or three-dimensional, but with a special axisymmetric geometry. So they are both steady or they could be traveling, let's say, but this is the same as steady in a moving frame, and one can consider also the effects of vorticity, but the main issues are already present in the absence of vorticity. So the main subject of the lecture is to give a description and characterization of all possible singularities in this stationary elliptic free boundary problems, but I will only start doing that from the second lecture. So for the moment I will give a detailed description of both problems, how they arise from the fluid dynamics equations. I will give an overview of the existing results on the 2D problem, which is like a very classical, dating back more than 200 years, so to say, and seems like a fundamental problem in fluid dynamics. By contrast, there has been relatively little work on the three-dimensional axisymmetric problem, and so I will also present quite a range of open questions about these problems. Okay, so let us think about the image of the ocean. So what? I also think of a picture of some waves and so on. So what is going on there? So there is a water region which is moving in time. So the surface changes, and the water inside the region has a certain velocity which also changes in time, and there is air above the water surface. Okay, so yeah. I should maybe not. So it is a very natural question, and which is, I mean, describing the evolution of the free surface and the motion of the water particles is a problem which is of great interest, let's say, for engineers, physicists, and so on. And there are like hundreds, or if not thousands, of papers on such topics. So this is a huge area of research. But it seems that is not so well known in this free boundary community, so especially among pure mathematicians. So this kind of questions are quite well known among applied mathematicians. Okay, so some questions and comments about the references. So for the main topics about the singularities and so on, so there are these 3 papers of myself in collaboration with Georg Weiss. So the third one has been accepted, and but it's only available on the archive. And we have, so I overlooked uploading the newest version. So I asked Georg to upload the version 2. So hopefully that will be live in a couple of days. So if you are interested in reading this kind of thing, it's a good idea to wait for the second version. And then the other references are for background only. So I have listed a couple of books. Well, one like 10 years ago, and the other quite recent, about water waves, and some of the maybe more interesting papers. But compared to the list on the website, so there is I am including here a new paper. So there is a survey by Walter Strauss published in the Bulletin of the IMS in 2010, which actually this is what I would recommend as a starting point for anybody interested to get some background information about the problem. Okay, so going back to the water waves, so the problem in general is 3-dimensional. Yes, so the ocean is 3-dimensional. And although here I have started directly with the 2-dimensional problem, so really the equations are the 3-dimensional Euler system. So water is usually considered to be an inviscid fluid. So the dynamics is described by the Euler equation rather than Navier-Stokes, and also it is usually assumed to be incompressible and moreover with constant density. And so the key point is that it is a system. And what makes special the two problems that I am considering is that in those situations, and maybe only in those situations, so can be reduced to a PDE for a single function. So all questions that I will be addressing, it makes sense to, well, a lot of them to ask them for fully general solutions of the Euler system rather than these special geometries. But yes, so this simplifies. I mean, this is essential for the analysis, that everything can be reduced to some to free boundary problem for just one function. And so in the first part of the lecture, I will describe how one does derive that equation. Okay. So so let me start with the. So I will concentrate on the 2D problem, and at the end I will go more briefly about how you derive that equation in the 3D axisymmetric case. So how does so first of all, how does well, this is basic for anybody who has seen fluid mechanics, but maybe some people have not. So how do you regard as a 2D flow as a 3D flow? Yeah, because in reality, of course, the fluid domain is 3-dimensional. So what I have here in the plane, so which we should imagine that it happens in the plane of the board. So we have the x and y axis like this, and then there is the third axis z, which is perpendicular to it. So like something coming out of the board, and the fluid velocity at every point in space so will be a vector v, whose components in general are u, v, and w, calculated at location x, y, z, and depending on time also. So with u in the x direction, v in the y direction, and the w in the z direction. But for 2D flows, so we have that w is identically 0, so there is no motion perpendicular to the plane of the board, so to say, while u and v are independent. So u is u of x and y, and v is v of x and y, which is, so to say, they are independent of the third coordinate. So this two-dimensional thing is just a cross-section of the in the three-dimensional problem, and well, so this is the connection as I have explained it here. Okay, so the fluid domain has, well, in 2 dimensions, which we are discussing here, so has a free surface, which is, for simplicity, assumed to be a graph for the moment, although it does not have to be, so it can be a curve in a parametric form. And so this is the interface. So here is the water region, and above is the air region. So this curve changes in time. So it's the graph of a function eta of t and x. So the fluid domain varies. I am assuming for simplicity that the water has a finite depth and a flat horizontal bottom. So this is important, located at the vertical coordinate minus d. So in the fluid domain, the motion of the water is described by the Euler equations. So which I suppose most of you have seen. So these are for the velocity field u and v, so which are functions of x, y, and t. And there is also a pressure p. So we have the Euler equations, material derivative, and so on, of the velocity equals the minus the gradient of the pressure. And I am also assuming that the only external force acting on the fluid is gravity. Yeah, so water is heavy. And this contributes to a term little g in the equation. So this is due to gravity as the only external force. So incompressibility condition is modeled by this requirement on u and v. And then we have certain boundary conditions. So at the bottom, every particle has to move horizontally, so cannot pass through the solid bottom. So the v is 0, the vertical component of the velocity is 0, while at the free surface, so we have this kinematic boundary condition that the same particles always always form the free surface, or so to say, the normal velocity of the surface is equal to the normal velocity of the fluid particle. So this is a standard condition. And also the pressure in the fluid has to be in equilibrium with the pressure in the air. So it equals a constant atmospheric pressure. Okay. So this we can regard, for example, as an evolution problem. So one is given an initial position of the surface and some initial velocity, and one can ask the question, okay, so what happens to how does the fluid evolve, and so on. And there has been a great recent progress on this kind of question. So it's the kind of results that one would expect. So for reasonable data, there is a short time existence and uniqueness, so to say, for irrespective of size of data, while if everything is sufficiently small, so the surface is almost flat and the velocity almost 0 initially, then there is a global solution. So these are very, I would call important papers, and some quite technical, some of them like 100 pages long, but it's not what I'm going to speak about. So what we're going to concentrate on is only the traveling wave problem. So in which the so the surface, rather than having an arbitrary dependence on x and t as before, so it has this traveling wave form. So it is a fixed function depending only on the difference x minus ct. So if you look at the wave, so you would see, and ignoring the motion of the water inside, so you just see a translating shape. Similarly, for the velocity field and the pressure, so rather than depending on x, y, and t, so completely arbitrarily, the dependence of x and t is only through the form of the only on this combination x minus ct and so on. So all our functions depend only on two variables, x minus ct and y. And so instead of x minus ct, I will use x. So in this way, we eliminate time from the problem, and we are left with a stationary problem. And what do the equations become? So if one looks back at the previous slide, so the t derivatives will become minus cx derivatives. So this will become something like u minus c ux. So subscripts denote partial derivatives here, plus v uy equals minus px and u minus c vx plus v vy equals minus py minus g, with ux plus vy equals 0, but which I can also write it as u minus cx plus vy equals 0. So now this last condition implies that there exists a function psi such that u minus c equals psi y and v equals minus psi x. Yeah, so this is just calculus. So you have a pair of functions whose partial derivatives sort of agree. So they come from a gradient, and so there has to be this minus sign. So this is standard fluid dynamics. So this function psi is called a stream function.
Is this the only reason you take two-dimensional, that you can transfer it to a level line? Or?
This is exactly what I said. So the system can be reduced to PD for a single function. So my aim is to get some equation only for psi. In general, it's not possible. So both in 2D and in 3D axisymmetric, it's possible to do that. Okay. So in these equations here, one can get rid of u and v and replace this by partial derivatives of psi. And we try to get rid of the pressure as well. And that we can do, you see derivatives here. So to get rid of it, so you differentiate the first with respect to y and the second with respect to x, and say that those things are equal. And so in this way, so we get to this equation here. So now what this is telling us is that the functions psi and delta psi have parallel gradients. So this sort of means that they have the same level sets if the gradients are not 0, or one is a function of the other. So this equation there that I have, delta psi x psi y equals delta psi y psi x, is closely related to the fact that there exists a function gamma of one variable, so function of one variable such that delta psi equals gamma psi, and I can put a minus. Okay, so now in this direction, so this implication is always true. So if you have something like that, you get that. But then the other direction as well, under some extra assumptions, for example, if psi y is different from 0, or locally if the gradient is not 0, or something like that. So, so although this is the equation that we would really like to solve, so it is automatically satisfied whenever the Laplace of psi is a function of psi, and this function can be anything. So it still gives us a solution of the Euler equation. So now in fluid dynamics, so this quantity omega Vx minus Ui.
Is it possible to determine gamma by some conditions, side conditions?
It's a very good question. Yes, but I will. Yes, so this is. So, yeah, I will say something about that very shortly. So, about what is the meaning of vorticity and so on. So this quantity delta psi is the vorticity, and basically describes the local relative instantaneous spin of fluid particles. Okay, so let me give you an example to see what vorticity means. Or maybe I can leave that for a bit later and try to finish the derivation of the equation. So in the fluid domain, there we need to have this PDE here. So now once gamma is known, one can easily check that if we consider the primitive capital gamma of little gamma, this is what it means. Then, if you add the pressure to this expression, half gradient psi squared plus gy plus gamma psi equal constant. So this is Bernoulli theorem, but you can check it by direct calculation. So how do you check that the function is constant? So you look at the partial derivatives, and so you see you get px, py, and all sorts of things. So you get exactly the equations that we had here. Okay. So the we had some boundary conditions on the top and on the bottom. So on the bottom we had that vertical velocity is 0, psi x equals 0, so which implies that psi is constant on the bottom. While on the free surface, if you write down what those conditions mean, so they turn out to be exactly that psi x plus psi y eta prime equal 0. So which is also exactly the fact that psi is constant. So this stream function is constant both on the bottom and on the free surface. So here I have the so repeating, so this semi-linear equation involving the Laplace equation on the fluid domain, constant Dirichlet boundary conditions on the bottom and on the free surface, and so we are free to choose them as we like, and I choose 0 on the surface. And then the other, we call it M, so we don't know what it is. And then the other condition was that the pressure is constant on the free surface. Yeah. But because this expression is constant in the fluid domain, so we get that this gradient squared plus gy plus gamma psi is constant. But psi is constant also on the surface, so this is also a constant. So in the end, we are left with this expression here being constant on the free surface as well. So a constant Q, so to say. And these are the equations for traveling water waves expressed in the stream function formulation. Okay, so now one can look, for example, or it is easiest to to look for periodic, spatially periodic waves, which is like what I have drawn in this picture. So the surface is periodic. This function psi is also periodic in the horizontal direction. But one could also consider solitary waves in which this surface decays to some constant level, and instead of the bottom being flat and horizontal, we could imagine the fluid domain extending to minus infinity. So that is the infinite depth problem. So this is the gravity wave problem, but one can look at a more general problem like capillary gravity, in which the pressure at the interface is not constant, but the difference in pressure is proportional to the mean curvature of the interface. And then here in the right-hand side, rather than having just constant, we get a curvature term. But that is a different problem, and a different kind of results are available. Okay. Yes, and as you are going to see, the most of the existence results on this problem are based on a bifurcation theory. So in bifurcation theory, you have an unknown and some parameter, but only one. So that's why it is usual to consider, so we have a lot of constants here. So all of them are fixed except for one, which will remain as a parameter. And so so we have the freedom of translating this thing vertically upwards. So we can choose either Q to be 0 or D to be 0. Okay, that's not so relevant. If we choose D equals 0 and leave, so we can leave Q as a parameter. But then this gamma, we regard it as a given. So it can be arbitrary, and it's a natural question, where does it come from, what's the most interesting gamma, and so on. But for mathematical theory, it is easiest to assume that the nonlinearity in the semilinear equation is given. Okay, so now what about the meaning of vorticity, and whether this problem has... please.
What do you mean that the vorticity function gamma is given? Who is giving it to you?
We can prove, so this problem has a huge number of solutions. So no matter what gamma is, I can construct a very large family of solutions. So it's not, I mean, if I could prove something only for very special gamma, you'd be motivated to ask why that and not that. But yes, no, but it's a very important question. So where does it come from? And actually, it's more natural not to assume that it is given, but this is like a subject of current research, I would say. So I can't give a short and quick answer now. So first, so we can ask, are there any solutions at all for this? And these are the trivial waves in which the free surface is flat and the motion is horizontal. So psi does not depend on x, only on y. So one can imagine, yes, so in some sort of river with flat free surface, and all water moving horizontally. So water on the same level always has a constant speed, but maybe the speed varies with height, and so so we can see, so the equation is minus psi yy equals gamma psi. Psi y is constant even only if gamma is identically 0. This is called irrotational flow, and in a way it's maybe the most important, so to say, occurs often. So yeah, so you can see, so if this is 0, then psi y is constant, but if there is something non-zero here, then psi y varies. So in irrotational flow, so all water, no matter of the height, moves with the same speed and so on. But in a wave with the vorticity, so the horizontal velocity varies with height, and this is so vorticity. So I might call this shear flow. Yes, and we can see that two particles who are maybe at the same vertical position, in a short time, one moves here and the other here. And so a vertical segment has rotated somehow. Yes, so vorticity, this is the meaning. So some sort of particles rotate with respect to each other in the motion. So, and for any gamma, we can find a family of such trivial parallel flows. And then anything that can be said about non-trivial waves is waves which are not like this is interesting and so on. But, so this is a very, very classical problem. Was first, well, not first, but to which substantial contributions have been made by Stokes. And he actually had a great vision, so to say. So he said that, so in his opinion that he wrote in his paper, is that, well, so there is a family of waves connecting a trivial wave with flat free surface to a wave of very special shape, which here at the highest point is not smooth, but has a corner of 120 degrees. So he said that there is a family of waves parameterized by height. So at the beginning, yes, so height being the distance between highest point and lowest point on the free surface. So starting from 0 height, and then there exist waves of greater and greater height. And then there will exist a wave of greatest height, which at the highest point will have stagnation point, so 0 velocity, so equals 0, 0. And that wave is not smooth like all the others, but has a corner of 120 degrees there. And so where does that idea come from about this angle? So as I said, this is a free boundary problem because we have two boundary conditions on the free boundary. So, and the curve is not known, has to be determined. And so yeah, so the curve is like this with psi equals 0, and the gradient psi square equals q minus 2gy. So g is a constant, q is a constant, y is the vertical coordinate. So if a wave is monotone like this, then the gradient is smallest when y is larger. So gradient is always smallest at the highest point, and throughout it is bigger. And the existence of a singularity is connected to the fact of a gradient being 0. Yeah, so for people who have seen this kind of thing, it's the standard. So if we have some Dirichlet and some this kind of, so if the gradient is not 0, we expect the curve to be smooth. But if the gradient becomes 0, maybe a singularity is possible. So that's the main idea. So for all of these waves, the gradient is never 0, so they are smooth. And once you reach the highest, so it has a point with a 0 gradient, which necessarily has to be at the top. And at that point, so it's not smooth, but it has lateral tangents making an angle of 120 degrees. So this was Stokes in the 1800s with this picture. And he was able to say something only about small amplitudes, so small perturbations of this thing, and something about this wave, doing also again some asymptotic expansions around this point. But no, well, so there wasn't really any rigorous argument to suggest that this family of waves with larger and larger amplitude exist and going from here to here. So we can see that there are three different issues in Stokes' picture, so to say. So the existence of these smooth waves, the existence of an extreme wave with zero gradient, with stagnation point, and then a regularity issues. And this statement that I refer to as the Stokes conjecture, you saw it in the title, in the abstract of my talk, is essentially the statement that gradient equals 0 at the point implies corner of 120 there. So it's a local question. So you know that you have a free boundary with this Dirichlet and Bernoulli condition and some PD and so on. And the fact that it's the solution has, the function has zero gradient, you want to deduce that there is a corner of 120. Okay. So for irrotational waves, which are all that Stokes had considered, so small amplitude waves was proved in the 20s by Nekrasov, Levy, Civita, Struik. And then the existence of smooth but large amplitudes, so which are not perturbation, in the 60s by Krasovsky, and then Keddy and Norbury, and Amick and Toland, a refined result. Yes, so and the existence of extreme waves with which have stagnation points was proved by Toland in '78, and a slightly simpler proof by MacLeod, and the Stokes conjecture again by Toland with Amick and Frenkel, and simultaneously and independently in Russia by Plotnikov. Yeah, so this was Stokes' program was completed by the 80s. And the ideas for this irrotational wave, so zero vorticity, delta psi equals 0. So harmonic function in 2 dimensions. So everything was based on complex analysis. So you reformulate the problem over a fixed domain by conformal mapping, then you transform it to an equation on the boundary involving Hilbert transform, Dirichlet-Neumann operator, and so on. Extreme wave, well, global bifurcation theory for smooth waves, extreme wave as a weak limit. In the integral equation, you do some blow up and classify the blow up profile, and this is how the proof was done. But that was, 30 years ago. But it is natural to ask the same questions for waves with vorticity. Yeah? So where instead of harmonic, you have gamma psi. So all the questions still make complete sense, and the methods in principle work, but just the initial step of using a complex analysis does not work, and so you need to do something completely different. So on the theory of waves with vorticities, so there is an explicit example of a Gerstner, small amplitude waves, Dubreuil-Chacotin, and large amplitude waves, Konstantin and Strauss, 2004. And the result is this. So for any function gamma, if the period is large enough, then you can find a set of solutions which is connected in a certain function space. So they are all smooth, but the y derivative of psi, so which is always smaller than 0, approaches 0 somewhere in the fluid along a subsequence. And then this suggests that maybe there is some hope that, that in the limit we can get also a wave with a 0 gradient. So, and about that subject, there is a paper of mine which contains some partial results, like some sort of a strategy. If you could prove some a priori bounds, then I gave away how to pass to the limit and some properties of the wave, but essentially, yeah, so it did not solve the problem in any yes, maybe half of what was needed. And then to complete this system of extreme way, so I have been working with Ovidiu Savin, and but yeah, so there isn't anything published yet. So if one of you can solve this problem in the next couple of days, so you'll be the first to claim the existence of extreme waves. So, however, the regularity issues, so we have I have solved in this paper with Weiss, and so this is what I am going to discuss in the next lecture. So, proof of the Stokes conjecture for water waves, and for yes, similar results for 3D flows. But for the moment, I want to still speak about so what is known about this kind of Stokes program, and what methods have been used, and what are some of the important open questions. So the regularity has been essentially settled, but the existence and properties and so on are so this is where the open problems lie. Okay, so one of the difficulties of the problem is that it's a free boundary problem, and as such, well, so one could use maybe variational methods, but this has not been done successfully. So the approach of Konstantin and Strauss was to do a change of variables to transform the problem to one in a fixed domain. So we have this wave with psi equals 0 and psi equals m, and for that it is necessary to assume that psi is monotone in the vertical direction, let's say smaller than 0 for simplicity. Then instead of seeking psi as a function of x and y over this one unknown dom. Yeah.
Why do you assume monotonicity?
At the moment, I'm not assuming it will come out by construction. So the
so this is one choice.
This is one choice, but the so the all waves for which existence is known are monotone and symmetric by construction.
The psi y is the horizontal velocity.
Well, so monotonicity on the one hand is about the free surface, okay, but you asked me about this. No, so this just ensures that all the level sets are graphs.
Oh, I see. Okay.
But yeah, so one of the open questions is to construct waves for which maybe the level sets are like this, contain the, yeah, so that's the, but for this kind of, so it's a requirement of the method to assume some sort of, so instead of seeking psi as a function of x and y, we say, so let us seek y as a function of x and psi. So this is sort of a hodograph transformation or something like this. And so we exchange dependent and independent variables, and then this x and psi, or minus psi maybe, so x is can vary over the real numbers, and psi over between these two values between top and bottom. So what did I write there? Yeah, minus m. So the new variables x and psi are over a fixed domain. But one has to transform the equation. So instead of the Laplace equation, we get this sort of mess that you see here. So it's their notation. So so instead of y as x and psi, they call it, so x you denote it by q, psi by p, and y by h. Okay. And then you get this this equation, but it is in a fixed domain. H0 on the bottom, and this comes from the Bernoulli condition on the top. And this is a quasi-linear second-order PD. So we see second derivatives occurring linearly, and with the coefficients which are involve first derivatives, but this is always an elliptic operator, so quasi-linear elliptic equation in a fixed domain. Yes, so in this way you can use so they use the functional analysis. So you formulate the problem as an equation involving operators between Banach spaces, and so you want to find zeros of some function between Banach spaces and so on. But so this formulation is not suitable to describe extreme waves at which the y derivative is 0, and indeed it cannot describe critical layers and so on. So this is something one would like to get rid of, so assuming the monotonicity of psi in the vertical direction. Yes, so and now I want to highlight this global bifurcation theory approach, so which is what led to these results for existence of smooth waves. I mean, because it would be good, and if there were one could give other proofs of existence based, for example, on variational methods and so on. Yes, so I will recall the main theorems in bifurcation theory now. So first of all, so this equation can be regarded as a function defined on R. So this is where Q lies, and times so where H lies. So this maybe we can use a Holder space C3 alpha of the rectangle, and with values into C1 alpha of the rectangle cross. So if we take two derivatives here, so we get C1 function in the and then times C2 alpha on the top of the rectangle. This is an operator equation between Banach spaces in such a setting. So we can draw a picture. So this is Q, and this is H, and one has a curve of trivial solutions, a curve of trivial flows, which are those waves which are parallel and like this. So there is a one parameter family of very, very simple solutions, and you want to know well, whether there are other solutions as well and how they relate to those simple solutions. Okay, but by a change of variables, so it's useful to take a more abstract approach. So what if we had a function defined on R cross X with values into Y, or actually have defined on a subset, open subset of R cross X with values into Y, or these are Banach spaces, and I would like to solve the equation f of lambda u equals 0. So lambda parameter real number, u an element in the function space, where it is known that f of lambda 0 equals 0. So so it's sort of we have a line of trivial solutions. So in the preceding it was a curve, not a line, but you can reduce everything to the case of yes. So 0 is a solution for every value of the parameter. And these are, so what I'm going to describe are really very, very classical results, but maybe not so well known in this community, and maybe somebody can find some new applications to different problems. So first there is the local bifurcation theorem of Crandall-Rabinowitz. So if on this line one finds a point at which the linearized operator with respect to x has a one-dimensional kernel, range of codimension 1, and a certain transversality condition is satisfied, then the solution set in the neighborhood of this point consists of, well, union of this line and a small curve here. Yeah, so this is perturbation theory. So you check these conditions, and if they are true, you get some solutions which are close to zero. So that's okay, well known, very well known, has been used in a lot of problems. This is what is used in this problem here. So then global bifurcation theory of Rabinowitz, so to say, again very old, but gives you the existence of large amplitude solutions. And the assumptions are, so this is based on degree theory, Leray-Schauder degree. And that requires the equation that you want to solve as being that of a fixed point of a nonlinear compact operator. So this is an essential assumption. So if your equation looks like this, and under this assumption, then this local curve assumed to exist can be, well, and the problem is only defined in an open set, so not in the entire space. And this piece of curve has a global continuation, maybe with splitting into pieces and with some other solutions. So it's a connected set, but at least one of the following happens. So either goes to infinity along a subsequence, or it goes to the boundary somehow along a subsequence, or it returns to the line of trivial solutions. And so it's a global. So these are results not by perturbation, but and you try to rule out this possibility that it returns, and you want to see what happens well, if the solution set approaches the boundary or if it goes to infinity. And you would like to get that it goes to infinity. So this is very classical, but it does not apply to the previous problem because the equation is not a fixed point of a compact operator. So what Konstantin and Strauss used was this refined version of Rabinowitz due to Kielhofer in '85. So again, you want to solve, to find a non-zero solution of an equation. And but now you don't need to have that your operator is compact perturbation of identity. I mean, the conclusion is the same, but the assumptions are weaker. So you still need to have some compactness property, so-called proper. Inverse image of compact is compact, and you need to have some spectral property of the linearization. So linearization must be Fredholm of index 0 and something about the spectrum and so on. And then you get this large amplitude solutions. And so this is what Konstantin and Strauss used for their results on this equation. Yes, so as I mentioned, so there has to be some compactness for this kind of operator, and this is based on Schauder estimates, and so it's elliptic theory. So this elliptic PDE theory combined with global bifurcation theory. Okay. So this is yeah, all I wanted to say about the smooth solutions. That the existence has been proved by this kind of global bifurcation theorems that I mentioned. So now some open problems. So the abstract method gives very little information on the solutions constructed. So one can ask, for these smooth waves, can we prove a priori bounds? So does the height of the wave remain bounded? Does the fluid velocity remain bounded? And can one pass to the limit somehow? So can one really get extreme waves? So this is something I have, as I said, I have been working on with Ovidiu Savin. Okay, and then what is annoying about, well, most annoying about this construction is that it does require indeed the psi y less than 0 or greater than 0 everywhere. So it would be good to have a formulation which could one could get waves with the critical layer, so the level sets are like this, or even where the surface is not a graph but overhanging. So even in the case where gamma is constant, there are numerical computations that people have done saying that such waves exist, but there is no mathematical theory, so this is something I'm also working on. And then in this theory, so there is no uniqueness result whatsoever. Yes, so well, I think I skipped one slide of the bifurcation. Yeah, I'll get back to that shortly. So so there are these curves of solutions, but it is not known whether there is just one curve and so on, or maybe it splits into different pieces, or whether there are any other solutions, or maybe there are solutions which are isolated from those on the curve. So uniqueness is completely open. Okay, and then existence by variational methods. So the problem has variational structure. So those familiar with this paper of Alt-Caffarelli and so on, so we'll have recognized this kind of thing. But so if one is looking for periodic boundary conditions and psi equals constant, and one is looking for psi equals 0 here, so it is to be expected that global minimizers are flat. So if you do global minimization, you don't get in this kind of so all these papers are nice and good of Caffarelli and so on, as far as regularity is concerned, but for existence for this kind of problem does not say anything. And then there is the issue of well, so how do this what is the role of these steady solutions in the context of time-dependent flows? So this is stationary, but if one perturbs it a little bit, so does it remain closed, or does it, yes, so stability, instability, but this is completely different issue. And yeah, so in 1 minute, so yes, I will not move to the other problem with axis symmetric. I will start next. So this is just a few slides, but better not to start now. Let me get back to the bifurcation theory. So I want to, I should mention also something quite interesting. So this is these are some very nice results, but which can be found in the book by Buffoni and Toland. So when the operators involved are real analytic, a lot more can be said about the solution of nonlinear equations than can be said by means of degree theory. So this is a completely different theory. And maybe, so one can say it involves some ideas from algebraic geometry or something like this. So it is a bit technical, but the so while topological theory, so based on degree theory that I mentioned earlier, so gives the existence of a connected set of solutions, but no other information. So the real analytic theory gives the existence of a path connected set, and which contains a global curve. So we have this line of trivial solutions, and this small piece of local curve by Crandall-Rabinovitz. So the theory, real analytic theory, first set up by Dancer and refined by Buffoni and Toland, so really does say that this can be continued globally as a curve with certain behavior and so on. yeah, so and the more refined, so either returns to the original point or goes to infinity or to the boundary. But the question is, the issue is that one gets a curve rather than just a maybe messy connected set and so on. So these are not necessarily the only solutions. So the curve can intersect other manifolds or other can split into several pieces and so on. But yes, so one has a curve with a locally real analytic reparametrization. So my impression is that a lot of people, well, or some people are using local bifurcation theory in free boundary problems. So you have some trivial solutions and you perturb them and you get some nearby solutions. So the message is that so if your equations have a certain compactness structure, so again some compactness, Fredholmness of the linearization, so the this local curve can be extended globally, and then there are a lot of questions that one can ask: what happens along it, and with yeah, the solutions that one finds. So this is about the existence of smooth solutions. Passing to the limit and getting on extreme wave, I'm not going to discuss. So most of the next lecture will be devoted to this regularity questions about Stokes conjecture. So the identifying the behavior at the singularity in the both in the 2D problem and in the 3D axisymmetric problem. But okay, so I'll finish here for now. Thank you.
So it is time for afternoon tea, but are there any quick questions?
So this 120 degrees angle is always pointing up?
Yeah, so it has always been assumed that water is below air, and so the what? Yeah, but in the
So if water
yeah, it's like that.
It points up.
Yeah, yeah.
It's never on the trough.
No.
Okay, so any other questions over tea? We reconvene in half an hour.